Yeah. So starting with session two, I have mentioned few things in last session, such as what exactly are nanomaterials and why do we use nanomaterials, all those things, and also there are what are the different kinds of magnetic materials we can see. So, wait a minute. Yeah. So, moving on to the different types of nanomaterials that I have explained before. So, starting with, let's start with what's the size. Yeah. The first one will be the zero-dimensional nanomaterials. At first, I have zero-dimensional nanomaterials. Then I have one-dimensional nanomaterial. Then 2D, and then 3D. So what we have discussed before is these things described. So for example, if I say, if I'm telling like zero-dimensional nanomaterial, so what does that mean? So zero-dimensional nanomaterials means there is no, so for example, we have three dimensions, right? What is X, Y, and Z, right? These are the three axes. Now, what do I mean by zero-dimensional nanomaterial is, so all three axes are in my nanoscale. Right. So there is no axis. For example, I have a quantum dot, or I have Florence, or you can even call them buckyballs. Right. So quantum dot is nothing but, so all three dimensions, like the X, Y, Z, all three dimensions are in nanoscale. And what about one dimensional nanomaterial? So one dimensional nanomaterial mean 1D nanomaterial, right? So one dimensional nanomaterial. So what do you mean by one dimensional nanomaterial is all other two dimensions. For example, I have X, I have Y, but not the Z or any other direction. For now, I'm only taking my X and Y, right? So X and Y are both axes. Now, if my one of the dimension is not in nanoscale, then I call it as a 1D nanomaterial. Now, what are the different types of 1D nanomaterials? I have CNTs. We can call it as a CNTs, or nothing but the carbon nanotubes. And these characterization and making techniques will be explained uh, in further lectures. Okay. Yeah. So sorry again. So first we have CNTs, that means the carbon nanotubes, and these making techniques will be explained in further sessions. So there are like very few like PVD, CVD process itself, and yeah. So after that we have one is single wall CNTs. That means you have very thin wall, and then if I'm saying about the multi wall, then multi wall is nothing but we have the code structure, and in one tube you have another smaller tube, so that's why we call it as a multi-wall CNTs. Don't worry about it, we will come to that, what exactly are CNTs, how they are made, what they are made of. You will see that it's just like giving you demonstration, that's all. So we have CNTs, yeah, and then yeah, these two are the, you can take as a nano rods, and nanorods, that means the whole material is bulk material. Inside you will, inside the rod you will find volumetric material, and then in nanotube you have, inside you will not find any material, it's a hollow tube, right? So then you call it as a tube and your rod, right? And then you have fibers also, nanofibers, right? And then moving on to two-dimensional nanomaterials. Moving on to two-dimensional nanomaterials. See, in two-dimensional nanomaterials, all you need is uh, a thin film, right? Even if you have a thin film, you can call it as a two-dimensional nanomaterial. Okay, right. And in two-dimensional nanomaterials, there are different types. The one you can form is a thin film. Thin film is nothing but you deposit. For example, you have a material. This is my surface. So on this surface, and if I want to deposit something, let's say I deposited one layer, right, of this thickness, like 2 nanometers thickness, or 2 nanometers to more or say 100 nanometers, 100 nanometers, right? So this thickness, we call it as thin film. Right? We deposit a thin film, and if that thin film thickness ranges in like 2 nanometers, 100 nanometers, we call it as a two-dimensional nanometer. Now you can even have what do you call a slab, right? See, in X and Y, this is X, this is Y. In X and Y, I have like large dimensions. There may be more than like zero point 0.1 mm, you know, and Y is also in the range of greater than 0.1 mm, right? But the thickness is less than 100 nanometers. You can take some slabs or some rectangular billets. These are the two-dimensional nanometers. Two-dimensional nanometers mostly you can find are like, what do you say, thin films. That's all. You will not find many other things, but yeah, finding these two-dimensional nanomaterials are also great because you have to maintain this third dimension very precisely to get to that nano range, right? And then in three-dimensional nanomaterials. So yesterday also I have explained. So there is a slight confusion. How do we understand three-dimensional nanomaterials? Right. There's this confusion with people. How do they understand this three-dimensional nanomaterials? Right. So let's say. Uh, so what does this mean? This means all my three dimensions are greater than 100 nanometers. Right. So all my three dimensions are greater than 100 nanometers. Then how do you speculate it, or how do you define it? Right. That is the most important thing because you do not know how do you define it. So let's say I have a matrix. Right. Let's say this is my bulk matrix, which is my bulk matrix. So it has a height of, let's say, 10 centimeters, and this is 5 centimeters, and this dimension is at 2 centimeters, right? So nothing is in nano range. Now, what if I try to incorporate, let's say if I'm trying to incorporate some press plates whose size is in nano range, right? Let's say I'm trying to incorporate these nano press plates inside the material. Let's say it is a random process. I just randomly inscribed my nanoparticles here, right? They may be anything. For example, so these are the things. Now, if I'm trying to inscribe some nanoparticles here, right? So these precipitates you can in solidification or in, how do you say, aging process. You can, some metallurgist can might relate this. So aging process or hardening process, you can call it as that also. And process, right? So what exactly happened here is, the people who do not know, I'll again explain them, because it will now or then come to you, because you have to understand this, right? So why not like explain whole thing? So for example, I hope everyone knows what exactly is a phase diagram. So phase diagram is nothing but uh, it's a geometrical construction where you will find what is the equilibrium phase, like whether it is a solid phase or liquid phase, you'll find that. So it is an equilibrium, it is geometrical interpretation of a thermodynamically stable diagram at a given composition and temperature. So for example, let's say I will take a amorphous phase diagram. Let's say amorphous is nothing but, not amorphous, sorry. So isomorphous. So if I'm talking about isomorphous phase diagram, then what do I mean is, let's say this is my temperature scale, and this is my composition scale. Composition scale, for example, if I take a binary alloy, right? So a binary alloy. Binary alloy is nothing but it is an alloy between A and B, right? So it is an alloy between A and B. That means you mix A atoms and B atoms. So for there are different types like lead tin system. You have silver and copper system, and yeah, it will go on. Like you have NIL system, right? So there are different types of binary phase diagrams, but one of the is, let's say, an isomorphous. Isomorphous is nothing but you add some A atoms into B atoms. It will remain as a single phase. Like for example, if I say solid phase, it will remain as a solid phase, and it will not even change this crystal structure. Right? If B is my FCC, and if you add A atoms, it will still be an FCC crystal structure. And the same goes for other side also. For example, if I have A material and if I add B atoms, then what happens? The same thing. If it is a solid phase, it will remain as a solid phase. And if it has FCC or for example BCC, then it will still be a BCC or FCC crystal structure, whatever the parent material is. So that is what we call as the isomorphous phase diagram. So for example, let's say this is my isomorphous phase diagram. Now, this whole region is solid and this above region is liquid. And this is the pure. Let's say this is A, this is B. So B atoms are being added. Is 10 weight percent, 20 weight percent, 50 weight percent, 80 weight percent, 90 weight percent is 100. That means pure B atoms. And you have pure A atoms. So A phase will have FCC. Let's say B phase will also have FCC phase. Now, if I try to add A atoms, so let's say this is my crystal structure. Let's say this is FCC, right? Let's say simple cable, not FCC. So if I try to add, these are all A atoms, right? If I try to add B, then B will be replaced by one A atom. That's all. There is nothing more. So this A atom will be replaced by one B atom. That's all. The everything structure remains same. Yeah, the lattice parameter will slightly change because the A and B has different electronegativity and different, yeah, electronegativity is sufficient enough to define who will attract more, right? So because electronegativity opposite electropositivity, so everything will just move back and forth, right? Now, if you're trying to add B atom to the A atom, so it will become richer in B, and finally you will attain P phase. So let's say at 0% B, that means it is a pure A. And if it's 100% B, then it is pure B. There is no A here. So it is pure A, this line, and this is pure B, right? Pure A, sorry, someone like, yeah. So pure A will have, say, pure A atoms will have a single phase, FCC. The same goes for pure B atoms, right? So B will have FCC. Now, pure A has a sufficient, I mean, one melting point. The same goes for B. Pure B will have some melting point, and you mix them, they will have a range of melting point, right? So 10 weight percent will have this amount, and 20 weight percent have this amount. Now, what happening is you will not have sharp melting, right? So pure A will have a sharp melting. You just go from solid to liquid. That's all. And same goes for pure B. You go from solid to liquid. If you have a mixture of solid plus, like for example, if you have a mixture of 90% of the A atoms and add here, yeah. So for example, if I have 90% of A and 10% of B, yeah. So 90% of A and 10% of B. So my melting temperature is here, right? So what is happening? What's happening here is you have a range of melting, right? There is no sharp melting now. You have a range of melting. That means you have this point and this point in the diagram, right? From here you can see 10%. So this is called liquidus line and this is called solidus line. In between, so below this, this is the temperature, right? You have temperature scale here. So below this, you have complete solid, and above this point, you have complete liquid. And in between, you have solid plus liquid. So slowly the solid, whatever you solid have, it will slowly start melting and you will get forming liquid. And when, yeah, this proportions, this ratio will first, yeah, decrease and this guy will increase. So this is what happened. In between, you have mixture of solid plus liquid. Now, where were we? Yeah. So why I'm like explaining these things is to understand what exactly is happening during precipitation, right? So how do you precipitate, or you do age hardening? Just like I have said before, you have this age hardening process. Yeah, it's age hardening process. With that means with time the material gets hardened, right? So if you draw a graph between hardness and time, or what I want time to mention, or log time, however you want to mention your scale, the hardness should increase, right? This is what it means. It may decrease after that. It depends on the property. So at first it should increase, right? So that is what we mean by age hardening process. That means with time you will have hardening. Now one famous alloy you see, this is in copper aluminum, right? You will have this precipitates, copper precipitates, or we call it as a nano precipitates, and they have very small size. Nano precipitates. We call them as GP zones. They are in range of nanometers. Just they are just like 2 to 3 atomic planes thick. That's all. Right. So, for example, we know the distance between two atomic planes is nothing but a bond length in in one direction. Right. For example, if I take 100, then that means it's nothing but a c-axis. Right. So again, I will mention this is A, B, C or X, Y, Z. This is 100. This is 010. This is 001. It's just nothing but I'm changing the axis. 100, nothing but x-axis I have 1 and everything is 0. That means A. 1 means A. That's all. Nothing else. The same goes for 010. That means the bond length is B. 001, the bond length is C. That's all. In FCC, you will have A equals to B equals to C. Everything is same. Now, let's say if I take my bond length is like 2 angstroms, just for an example, then 3 to 4 atomic plane thickness will be 3 times 2, which is 6. Or if I take like 15 atomic planes, then I have some value, right? Which ranges in nanometer scale. So these GP zones can be considered as the nanoparticles. Now, how do they form? Let's say this is my phase diagram. This is my composition. Let's not worry about the elements. Let's just say this is the composition, weight percent of B. This is A and this B. That in the right hand you will have B. Now, let's say I have phase diagram like this, right? Let's say this is some phase, like you have pure phase alpha, and here at last, like at some point, you have some phase called, let's say, an intermetallic. Let's know. I will not. When we discuss about intermetallic, I will discuss. So intermetallic is nothing but different types of phase which has a certain stoichiometric ratio. So, for example, CuAl2, right? It has a stoichiometric ratio where each copper atom is around. For each copper atom, you have 2 aluminum atoms, right? So let's say this is my precipitate, which is an intermetallic, and then you have a pure phase, which is an alpha. And now, for example, this is my weight composition of my alloy. Let's say 10 weight percent. Again, this is just for description. That's all. So at 10 weight percent, I have 10 weight percent of aluminum and 90 weight percent of copper. I'll find the exact. You can find the exact diagram. So I'm just taking the values, right? So here try to heat. So when I'm trying, sorry, at room temperature, let's say this is my room temperature. At room temperature, I have 2 phases, alpha and this guy. I have to see left and right. So the combination will be alpha and CuAl2. So this is my phase here. It is a mixture of phases. Now, if I try to increase my temperature above this point, right? Now, what do you have? The CuAl2 will melt and it will become alpha. That's all. So at this point, I have pure alpha. Now, what I try to do was when I try to normal cool it, again this you will have alpha plus CuAl2. Now I'm not going to normal cooling. I'm not what I'm going to do is I'm going to quench. Quench is nothing but I have rapid cooling. You just throw it in water or oil, which has better thermal conductivity, which can take thermal energy from it. Right. So yeah, I try to do quenching, which is rapid cooling. Then I can retain my alpha phase at room temperature. Right. So that is called as a retaining of phase. You just get the high temperature phase at low temperature. Now, what if I try to slowly heat that? So first, I was at room temperature. Then I went to the higher temperature T1, which is here. I tried to stay there so that the whole CuL2 gets melted. It melted, right? It get melted and have pure alpha phase. Then I suddenly try to quench it. Here I have a heating rate. So that's why there is a delta T divided by delta X. You have a slope, right? But not here. You have a very steep slope. That means there is a sudden drop in temperature. So I retained my alpha. This is called retention. Then I try to slowly heat it to, let's say, this is T2 temperature. Now, because I'm trying to supply some thermal energy, see, here alpha at higher temperature, alpha can take 10 weight% of atoms and still retain its same shape, like FCC or a single phase. Now, if I try to cool it down, the alpha cannot handle that much amount of B atoms, right? So B is aluminum. So copper cannot handle aluminum atoms when we decrease the temperature. So what copper does is copper just reject. For example, this is my alpha phase. This is my copper. The copper will reject the aluminum atoms outside. And these aluminum atoms will cluster and they will form CuL2. So that's what actually happens. Now what I'm trying to do is I try to quench it. So copper cannot instantly give it because it needs thermal energy. So I got a phase called as a supersaturation. Because at my room temperature, this is my limit for accepting of aluminum atoms. But when I try to quench it, this much amount of aluminum atoms cannot be rejected. So that's why we call it as a supersaturation region or supersaturation phase. Now, if I try to increase the temperature, slightly give a small amount of temperature, small amount of thermal energy, then these aluminum atoms will be rejected out and they will form a very small zones called GP zones. And that's how our hardness increases. And because these GP zones will obstruct our dislocation motion, so deformation is nothing but moment of dislocations, right? Now, if my GP zones are there, they will obstruct my GP dislocation motion. So material cannot be deformed. So that's why my hardness of material increases. And that's why we call this process as edge hardening process. So that is the basic whole theory behind this GP zones, edge hardening, and everything. So it's simple. It's just theory, physical theory. You just reach a high temperature where everything is a single phase, then quench it so that you retain that phase and reach a supersaturation. Then you slowly give some energy such that these small precipitates will form. Small GB zones will form. So that's how you increase your hardness. Right? So yeah, that is about yeah. Now these are my GP zones. And because these GP zones are in nano range, but when you consider the whole material, which is not in 3 dimension, which is not a nanomaterial, right? But their micro constituents or the other part of this material, you can easily call it as a micro constituent because that is a better word to define these GP zones, right? So these GP zones will act as a micro constituent because they are in nano range, but the whole material is not. So that's why we call it as 3 dimensional nanomaterial. Even though my material is not in 3 dimensions, at least my micro constants are in nano range. So that's why I call it as 3 dimensional nanomaterial. Right? Now moving on to the next one. Again the same. So all dimensions are at the nanoscale. My one dimension. See, so how do you define what is zero dimensional nanomaterial? One dimension, two dimension, three dimension. So zero dimension is nothing but all dimensions are at the nanoscale. One dimension is nothing but one dimension is not in nanoscale. That means this one, the rods. Because my here you can see my x and my y are in nano range, but not my z, right? For this part. So that's why I call it as one dimensional nanomaterial. Now moving on to two dimensional. In two dimensional, you can see my x. Let me remove this. Here you can see my x and my y. Oh, sorry. So x and y are not in nanoscale. So that's why it's called as two-dimensional nanomaterials. Two dimensions are not in nanoscale. Okay. Yeah. So, but what about the third dimension? The z-axis. It is in nanoscale. Nanoscale is nothing but less than 100 nanometers. Then we call it as nano range. Now, and because my z-axis in nano range, this material, or you can call it as a nano slab also. So we call it as two dimensions. Now, what about three dimensions? Just like I have explained before, even though all the dimensions are not in nanoscale, because the micro constants involving in that nanomaterial are in nanoscale, we call it as a three-dimensional nanomaterials. That's all. Now moving on to classification. So yeah, you can see I have gold nanoparticles. That means everything is nanoscale. Because if I just draw a graph and if I draw a sphere here, all things are in nanoscale. And this is called CNT. So CNT is so graphene is a single layer. Yeah, in two-dimensional nanomaterials, graphene can be considered as a two-dimensional nanomaterial. Why? Because the graphene is a very thin sheet made up of hexagonal rings of carbon atoms. Right, so carbon atoms are like this. So I can draw this more clearly. Say this is my carbon. Right, and this structure will continue. For example, if I give it, let's say, yeah, see. So you will have more or less hexagonal structure, so hexagonal rings that are attached to each other. So each carbon atom is bonded to three atoms. So actually the coordination number of carbon should be four. That means each carbon should have a bond with four atoms. So that's what we see in methane. We see in what do you call ethene, ethyl alcohol, anything. You can take anyone. So carbon must form four bonds. And what about if it doesn't form a four bonds? Then you have one dangling bond, right? So one carbon atomic orbital is still remained. So you have every carbon atom will have this dangling bond. Why? because carbon has to share 4 electrons to attain the octant electronic configuration. So there are only 3 bonds, but you do not have one bond in this structure, because you can see, you can even draw yourself and try to see. So for example, if I draw a 6-membered structure, see, anywhere you can see the carbon atom is bonded to only 3 atoms, right? Here you can get another structure, right? So you get another one. So carbon is only bonded with 3. That's all. So one remaining atom will be as a dangling bond. That means it is free. The electrons can move freely here to here. So these electrons can overlap for a picoseconds, and then these electrons can jump from here to here, and these electrons can jump from here to here, or jump from here to here. So there is a free motion of electrons on this graphene sheet, right? So that is one point you have to remember. Now what I'm trying to do is, so let me draw the graphene sheet itself. Right, so the electrical properties arises from 2 parts. One is coming from quantum effect, and another one is coming from the classical effect. Oh, I shouldn't say the classical effect, but that can be more explained classical. That's why I'm mentioning the classical. Right? Dimension, 2 dimension, and 3 dimension. So to understand these effects, let's first start with the density of states. Right? So if we start with density of states, then it will be easy to understand or see the picture what exactly is happening. Right, so let me start with 0 dimension, 1 dimension. Let me start with 0 dimension, right? So, yeah. Let me start with density of states so that people can easily understand. Yeah, that will tell about the quantum effects. So the electrical conduction of electrons in systems considered large in size compared with the nanoscale. Right? In this case, the conduction of electrons is delocalized. So it's again, if you localize an electron, it's against the uncertainty principle. So also in metals, we are considering delocalized electrons, like the electrons can freely move inside the material. For example, this is my bulk material, so electron can freely move in this bulk material, right? So Now, as they travel their path, the electrons are primarily scattered by various mechanisms, such as phonons, impurities, and interfaces, resembling a random walk process. So, however, as the system length scale is reduced, or if the system, like the dimension, one of the dimension is reduced from like 1 mm to a few nanometers, like less than 100 nanometers, then the system scale is reduced to the nano scale. The two effects come into picture. One is a quantum effect, where due to electron confinement, the energy bands are replaced by discrete energy states. So I will come to that in density of states in just a few minutes. So leading to the quantum effect, where due to electron confinement, the energy bands are replaced by discrete energy states, leading to cases where conducting materials can behave as semiconductors or insulators, and to the classical effect, where the mean free path for inelastic scattering becomes comparable with the size of the system, leading to the reduction in scattering events. Right? So in 3D nanomaterials, the three spatial dimensions are all above the nanoscale. So in three-dimensional nanomaterials, the three spatial dimensions are all above the nanoscale. Therefore, the two aforementioned effects can be neglected. However, bulk nanocrystalline materials exhibit a high grain boundary area to volume ratio, leading to increase in the electron scattering. As a consequence, nano-sized grains tends to reduce the electrical conductivity. In the case of 2D nanomaterials, with thickness of nanoscale, quantum confinement will occur along the thickness dimension. See, so if the dimension gets, if one of the dimension, like here it is 3 dimension, but here it is 2 dimension. Here the thickness is getting reduced below 100 nanometers. In this case, the 2-dimensional nanometers with thickness at nanoscale has a quantum confinement occurring along the thickness dimension. So simultaneously, the carrier motion is interrupted along the plane, right? So along the plane, the carrier motion is interrupted, because if you have 2 or 3 layers, then of different materials, then there is an interruption along the plane of the shape. In fact, as thickness is reduced to the nanoscale, the wave function of electrons are limited to very specific values along the cross section. This is because only the the only electron wavelengths that are multiple integral of thickness will be allowed. That I will be showing in a few seconds. Now. Yeah. So the electrons become trapped in that, right? So decreasing the dimension of the nanomaterial will have the discretization of energy levels, which will trap the electrons in that dimension. But trapping is nothing but allowing the electrons to only those certain energy levels, but not to the other energy levels. But that's not the case in the other dimensions, which are not in a nanoscale. So let's start with the quantum effect, right? So first, let's see what is the density of states. How do we define, or how do we so how did we get this function, right? So density of states function, right? So coming to that, see, for example, if this is my 3-dimensional particle, like 3-dimensional system, so let's say it is a cube. All sides it has length L, like this is length, and this is my breadth, and this is my height. So every side it is in length L, and electrons have the momentum K. Right? So we represent momentum. It's not a momentum; it's a wave number. So we represent momentum is equal to hk, right? H cut k. So let's say the momentum has a momentum p with wave number k. Then in the Fourier space, it looks like. Let me have a few more slides. So in Fourier space, that will look like Fourier space that will look like dots. And all these k values lie inside a sphere, and this sphere is called as Fermi sphere. All the k values of electrons will lie inside the sphere, right? So we are not applying any magnetic field. So if we apply magnetic field, and this sphere will turn out into a cylinders, and all the energy states will lie on the surface of the cylinder. Let's not it's again a different topic. Let's not go very deep into that. So let's say there is no magnetic field, B is equal to 0, and all the electrons lie inside the sphere. All the electron energy states lie inside the sphere, right? So now again going to the density of states. Now number of states available per unit volume with an energy E, that defines our density of states. Now let me write it. Number of states available per unit volume of energy E, right? So, and if I represent this function as gk, then gk dk will be equals to 4 pi square 4 pi k square dk. This is the surface area of the sphere times the thickness, right? So if I take a sphere of a thickness dk, now the volume occupied by one state, right? So that will be given by the volume occupied by one state. All the states of electrons are represented here, and they are represented as 2 pi by divided by 2 pi q by LQ. Now this is just a Fourier transform, right? Fourier transform 2 pi q by LQ. Now again coming to the density of states, as I have represented before, number of states available per unit volume, right? So the number of states gk dk divided by the volume of each state, right? That is equals to volume times 4 pi k square dk divided by 2 pi whole cube. Now we know energy is represented as P square upon 2m, and I have represented before what is P. P is equal to h cut square k square by 2m. You can represent h cut square or h square by 2 pi square, but h cut square is also said as the reduced Planck's constant, because the h value h square value is getting reduced, so it's just spelled as a reduced Planck's constant. Now again, what is k square? Now everything we have to represent in terms of E, because we want everything in terms of the real space thing, right? So in terms of energy values. So what is k square? K square will be E times 2m by h cut square. Now what about dk? Upon differentiating, this will turn out to be h cut square by 2m whole power 1 by 2 e power minus 1 by 2 times 2m by k square times d. Upon differentiating, this is the value you will get. It's simple. First you differentiate it, it will become 2k dk, right? And this dk will k will go that side, so you will have a dk value, and yeah, Now substituting this dk value in this equation, so let me write it. What was that value? 4 pi by 2 pi whole cube k square dk, which will be equal to 4 pi by 2 pi cube times 2m h cut square e 2m by h cut square minus 1 by 2 e power minus 1 by 2 d, and this whole thing can be represented as how? Ge dE, right? Instead of gk dk we can write it as gd, or density of states represented in terms of energy values, not k space, right? Now this ge will be equal to upon, let's see, yeah, 8 pi by, I'm not simplifying it because again it will take time, so I'm just writing it whatever the equations are. So 2 power 1 by 2 m power 3 by 2 divided by h cut cube and e power 1 by 2. This is all the constants. This is the mass of the electron, this is reduced Planck's constant, this is pi values, and these are constant values. So g of e is proportional to e power 1 by 2, right? And if I represent it in the graph, this is exactly a parabola, right? So, yeah. Here listed, so this is how it looks like. Looks like a parabola, right? Now this is for the 3-dimension material. Now what about the 2D, right? For 2D it becomes the surface. Now what happens with the surface? If we are talking about the surface, then that will become to, let me write it again. Now that g of k dk will be equals to what? Circumference 2 pi k dk. Instead of volume, it will turn out into area. So 2 pi divided square times L square. If I am just representing in terms of area, that will turn out to be L square. Now again going back, and let's just do the problem. Let's cut square k square by 2m, then k square will be 2me by h cut square. Again, what is k? K dk 2m de by h cut square. What is dk value? We know k is equal to root of 2me by h cut square. Now 2m by h cut square times de into equals to k equals to root, right? It's not, it's divided by root 2me by h cut square. Now this will be equals to, and because we have 1 here, so 2m h cut square whole power 1 by 2 and e power minus 1 by 2 times de. So this is what it is. Now substituting this, here we will finally arrive to the equation GE will be proportional to e power z. And G is proportional to e power constant. Then how does our graph look like? Our graph will look like this. Our graph GAD, and this is the density of states. Graph will look like. Let me show you how does it look like. Yeah, it will look like this. This is how it looks like. It's constant. Where our GED is constant. It doesn't depend on the energy E values. Right? Now going on to for one dimensional nanomaterials. For one dimensional nanomaterials, that surface now will become aligned. So our GK dk will be just dk divided by 2 pi by L, because we are only considering a one dimension, right? So this is how it looks like. Now again going back to that dk equation, dk is equals to x square by 2m whole power 1 by 2 e power minus 1 by 2 de. We substitute it there. Then it will simply be turned out to GE is proportional to e power minus 1 by 2. And again, how does our density of states graph will look like? It will look like this. It will look like as spikes in the density of states. Now, if again we can even do, if we try to do that for z-dimensional nanomaterials, there will be total discretization, and there is no continuous form. There is total just a discrete energy levels. For zero-dimensional nanomaterials, right? We show them here. That's how the density of states take place. Now again, going back to what are the density of states, what does it mean? So it means that these are the energy values that are allowed for electrons that can be in a material. For example, if I take a single hydrogen atom, these are the energy levels. So the discretization takes place. Right? So there is 1s orbital, there is a 2s orbital. Like one first orbit has a certain energy of electron, the second orbit the electrons has a certain energy. There is no overlapping, or there is no continuous energy values. Right? So that is all with the density of states. Now coming to the quantum confinement, right? So how for now we know what are the density of states, right? So moving on to the quantum confinement, right? How assign these, if we have a quantum confinement in any dimension, now how we are going to assign the values for the electrons, like energy value for electrons. For that there is a simple way. For example, if we take the particle in a box, for example, for a one-dimensional box. Let's say this is my box. This is one-dimensional box. Now again, why we are discussing this? Because only electron wavelengths that are multiple integers of thickness will be allowed. All the other electron wavelengths, Now, what is the wavelength? Wavelength of electron. Wavelength. We know the energy of a particle, of a quantum particle, is given by h, right? What is the h? H is a Planck's constant. Nu is a frequency. It may be the frequency of electron, it may be the frequency of photon. In this case, the frequency of electron. Now that frequency will depend upon the wavelength. Now our wavelength will define our energy, right? So yeah, going back to the electron wavelength that are multiple integers of thickness will only be allowed. All the other electron wavelengths will be absent. In other words, there is a reduction in the number of energy states available for electron conduction along the thickness direction. The electrons become trapped in what is called the potential well, right? That's why we are talking about the particle in one-dimensional box, right? So this is where the theory comes from, like the electrons become trapped in what is called as a potential well. So this is a potential well of width equal to the thickness. This is width equals to the thickness, right? In general, the effects of confinement on the energy for a two-dimensional nanomaterial with thickness at nanoscale can be written. For two-dimensional, three-dimensional, zero-dimensional can be written. For now, let's just assume for one-dimensional, right? One-dimensional discretization. For example, in 2 dimensions, there is one-dimensional discretization or one-dimensional quantum confinement, right? So that will be equal to, let's derive it now. We know we are deriving for the two-dimensional nanomaterial, right? So yeah. Now, the particle in a box, or let's say this is our potential well. Here the V is 0. Let's say this is our, next slide, yeah. So this is our potential well, a particle. Let me write it again. A particle in a one-dimensional infinite potential well of dimension L, right? So our length is equal to thickness of the two-dimensional nanomaterial. For example, if we are talking about a thin film, so that is its thickness and that is equals to L. The potential energy is 0. So let's write our assumptions. The potential energy is represented as a V here for now. So V is equals to 0. The conditions are 0 less than x less than L, right? And V equals to infinite if x is less than 0 or x is greater than L. Now it's these are very basic assumptions, and we assume the walls have an infinite potential energy to ensure that the particle has zero probability. Now again, what is the wave function? If we square the wave function, then that will give us the probability of finding that electron there, right? So if I represent any electron with the wave function psi, then if I normalize it or if I square it, will tell you the probability distribution or the probability of finding the electron at particular position, right? So we assume the walls have infinite potential energy to ensure that the particle has zero probability of finding being at the walls outside the box, right? So psi is 0. Let me write that too. Psi is 0 when v is equals to infinite. Now psi has some value when v is equals to 0. Right? Doing this will significantly simplifies our mathematical calculations later. So as we employ now, these are our boundary conditions, right? Represented here. Now let's solve the Schrodinger equation. What is our Schrodinger equation? It is a very well-known equation. Schrodinger equations have two terms. One, the kinetic energy term. Now this is my kinetic energy term. By x square. Another one is potential energy term. And also our wave function is a time independent, right? We are not considering the time because again it will bring complexity while solving our equations. So it is a time independent Schrodinger wave equation. Not time independent wave equation. So that will be equals to, one is a kinetic energy, potential energy, that will be equals to energy of right? And this is the energy operator, that is equals to the kinetic energy term and the potential energy term. Right? So again, we are not considering, we are just considering only one particle, and if we have an excitation energy, that again that will add some value here, not exchange interaction, not excitation energy. If we are considering 2-3 more electrons and we have some potential energy values, if we have some potential energy, then again this will bring more complexity, so we are not even considering that. So our exchange interaction term will be 0. Again we are considering the potential energy, as we are considering in between, potential energy is 0 between 0 to L, x is between 0 to L, potential energy is 0. So this wave function can be simplified to h cut square by 2m dou square psi x by dou x square equals to energy times psi of x, right? So how does it look? It looks like this: dou square by, it's a linear differential equation, now equals to 0, right? And we know the roots: a1 sine x ax plus a2 sine bx, right? Or cos bx. So the solution will look like this: a1 sine ax plus b1 cos bx. So this is my equation, y of x, right? So for this, it will turn out to be, now let me rearrange it. Now even assuming a constant, my constant k is equals to, now we know what is k. K will be equals to e to m by h cut square. This is our k. E m by h cut square, right? So let me write it as it. Let me denote it as a k square. Now, upon solving, seeing the from deriving from this will turn out to be psi of x is equals to a sine kx plus b cos kx. Now again, the boundary conditions. considering the boundary conditions. The solution to the Schrodinger equation we found above, we found here, right? We found here is the general solution for a one-dimensional system. Now we need to apply our boundary condition to find the solution to our particular system. And according to our boundary conditions, the probability of finding the electron at x is equal to 0 or x is equal to L is 0. Let's say, let's not make it equals to, let's remove this. At x is equal to 0 and x is equal to L, so wave function, our wave function dies, that will be 0. So when x equals to 0, for boundary condition 1, at x is equal to 0, psi equals to 0, right? So psi of 0 equals to a sine 0 plus b cos 0. Because psi of 0 is equal to 0, we had this first boundary condition, so 0 equals to a times 0 plus b. So b equals to 0. So we do not have any constant now. We do not have any constant. So our final wave function will be psi of x equals to a sine kx. Now we can solve for constant a. Now let's differentiate the equation. Dou psi by dou x equals to ka cos kx, right? And again, doing differentiation, double differentiation will turn out to be dou square psi by dou x square equals to minus k square a sine kx, right? Since, and also we know psi equals to a sine kx, this will again turn out to be dou square psi by dou x square is equals to k square psi, right? Now upon writing k, what is k? K is equals to 8 pi square me by h square upon 1 by 2. So if we plug this k into our wave equation, this psi will be equals to a sine 8 pi square me by h square whole over 1 by 2 into x. Now when x is equal to L, this wave function will be equals to a sine 8 pi me by h square into L. So this is our boundary condition 2. And now this psi is equals to 0, right? Because at x is equal to 0, our wave function dies, or we do not have any probability of finding our particle there. So sine, our amplitude cannot be 0 because we are considering the wavelength as it has a wave characteristics. So only thing that can be 0 is the extra, and we know that sin x, when sin x can be 0, so x can be integral multiple of pi, then we can clearly say that sin x can be 0. So what is our x here? Our x here is 8 pi square me by h square, not the reduced Planck's constant, 1 by 2 times L equals to n pi. Now where is equal to n, 1, 2, 3. Putting this back into our equation, that will turn out to be psi equals to a sine n pi by l into x. Now to go for a, we have to integrate it again. Integrate, we know the probability distribution. From 0 to L, we have the total probability distribution is 1, right? So integrating will give me 2 by L. Just a simple equation, can do it. So substituting there will be equals to psi equals to 2 by L sine n pi by L into x. And please know this is a standing wave equation, not the moving, right? The moving or the wave packet. So this is just a standing wave. Now how to find the energy levels, right? So energy levels will be given by the allowable energy levels, right? The allowable energy levels will be given by En equals to n square h square by 8mx square. Now, what does it show? The energy of the particle is quantized, right? Because in the density of states we have seen for the three-dimensional particle, the energy is continuous, but not here. Here the energy is quantized, right? Now, what are the possible values? The lowest possible energy of the particle is not 0, because this is called the 0-point energy, and it means the particle can never be at rest because it always has some kinetic energy, right? This is also consistent with Heisenberg uncertainty principle. If our energy of the particle is 0, then one either our position or wavelength gets infinite, right? So that's a violation of the Heisenberg uncertainty principle. Now again, what does this mean? What does n equals to 1 and n equals to 2 mean, right? Again, that is our question. So for n we have like this, and for n equals to 2 we have like it just shows the probability distribution, right? This is our wave function, and when we do the psi square, right? So it tells me the probability or the wave function distribution, right? Where the probability of finding the electron and the probability of finding a particle at a certain spot in the box is determined by squaring psi. We have psi and we squared it, so the probability distribution for a particle in a box at the n equals to 1 and equals to n equals 2 looks like this. Now, the number of nodes, the places, what do I mean by node? Again, where the places where the particle has the 0 probability, right? So this is my node and this is my anti-node. So increasing with the number of nodes where the particle has 0 probability of being located increases with increasing the energy, right? Because the more number of nodes will be added. For 0, for 1 here and here, for 2 we are at extreme positions and middle, and for 3 we have 2 positions and 2 extreme positions, totally 4. So as the energy of the particle becomes greater, the quantum mechanical model breaks down as the energy levels get closer together and they overlap, forming a continuum. Just what happens in this, the three-dimensional particles, the density of states is like this. So this continuum is the particle is free and can have any energy value. At such energies, the classical mechanical model is applied, as the particle behaves more like a continuous wave. Therefore, the particle in box problem is an example of standing wave. So how we get the standing wave, and also an example of wave particle duality, right? And so that is about the density of states and the quantum confinement, right? So for a two-dimensional nanomaterial with thickness at the nanoscale can be written as the quantization will turn out to be En equals to pi square h cut square by 2 ml square into n square. Now n square represent the discretization in which dimension. For example, this is a z direction, right? If this is my thin film, this is my z direction, right? So this is in z direction, and for other x and y direction it will simply be p square by 2n, right? So if I represent E total for two-dimensional nanomaterial, so the two-dimensional nanomaterial, the E total will be px square. So 1 by 2m px square plus py square plus, and this is equals to 1 by 2 ml square. You can take out pi square h cut square and that's it. This is our total energy. And L, what is L? L is the width of the potential well, and for if you are talking about electrons which revolve around the nucleus, so N is the principal quantum number here, and the basic assumption we took was the infinite depth potential well model. So and this is these two terms are for the unrestricted motion of electron. So let's assume the z so let's assume the z direction to be the thickness direction, and x and y in plane directions in which electrons are delocalized, right? So there is no localization, just I mentioned before, there is no discretization of energy levels, right? So in x and y direction we have delocalization of electrons. So under these conditions, the unrestricted motion can be characterized by two wave vectors. Instead of representing the px or the momentum, we can represent px as the momentum or the momentum operator as px square is equal to h cut square k square. Now representing that will be as E unrestricted, right? The unrestricted motion or the delocalization will be equals to h cut square k square by 2m plus h cut square ky square by 2m. Now E unlocalized will also can be represented as kf square, and where x and y are directions, so the energy corresponding to these delocalized electrons will be given by this, and it's also called the Fermi energy, which can be represented like this. Now the total energy of an electron, finally representing the total energy of electron in two-dimensional nanomaterial is given by P of n equals to pi square h cut square n square by 2 ml square plus h cut square kf square by 2. Since the electron states are confined along the nanoscale thickness, the electron momentum is only relevant along the in-plane direction, right? and also as a result uh, of, for example, if you are talking about the scattering by phonons, and impurities occurs mainly in plane, leading to 2D electron conduction. However, for 2D nanomaterials with nanocrystalline structure, the large amount of grain boundary areas, we have grain boundary areas, and also we have interfaces, right? So that can lead to more electron scattering or phonon scattering, so which decreases the electrical conductivity. And in case of one-dimensional nanomaterial, let's talk about one-dimensional nanomaterial. So, in terms of the one-dimensional nanomaterials, so quantum confinement will be along x and y directions, right? So if I represented the total energy of electrons will be equal to pi square h cut square by 2 ml square. If I assume a cube, that will be equal to mx square plus ny square plus h cut square kz square by 2m. This is for one-dimensional nanomaterial. Right? For example, if we are talking about CNTs, and if I represent for zero-dimensional nanomaterial, E total will be equals to pi square h cut square by 2 me mx square y square and u square. And there is a discretization in all three directions, on all three dimensions. So, and because of that, we have the discretization of energies. So, coming to here, and because of this, we have the discretization for the zero-dimensional nanoparticles. And because the electrons have to jump from one energy level to another energy level. So if we are talking about the density of states, we have this conduction band and this valence band. So for the conduction of electrons, the electrons should jump from valence band to conduction band. But in three-dimensional materials, it is easy because the energy levels are continuous. But for the zero-dimensional nanoparticles, we can make, because of discreteness, we can even create the insulators from metals. Why? Because of the spread of energies. There is no like continuous motion. The electrons have to jump from one energy level to another energy level. There is no availability of energy levels for electrons. Right? So that is another one. And these two-dimensional, three-dimensional materials are used in circuits, for external circuits as electrodes. For 2D and 3D nanomaterials, the ohmic contacts are possible. However, for zero-dimension and one-dimensional nanomaterials, the contact resistance between the nanomaterials and the connecting plates are usually high. So, thus one mechanism of providing conduction is through electron tunneling. This is another quantum mechanism, quantum mechanical mechanism where in infinite potential well, I have said before that the wave function of finding the wave function is zero. From 0 to L, we have wave function, and from after L, before 0 we have zero wave function, or the probability of finding the electron is zero. But it is not actually the case. The quantum particles actually tunnels from the barriers. So we still have the wave function, even though it is dying very fast. which is an exponential. It is an exponential term, but still the wave function exists after the potential energy. Well, it means the wave function doesn't drastically vary. So this is again the quantum tunneling is a quantum mechanical effect in which the electron penetrate potential barrier. So for an electron to tunnel from one metal to the another across an insulator, one of the metals, one of the metals must have the unoccupied energy states. So a simple way of achieving is to apply the voltage across a circuit to raise the Fermi energy, right, of one of the metals. In this fashion, electrons can tunnel from metal with highest Fermi energy to the metal with lowest Fermi energy, producing a current I in the circuits. So let me show you how it looks like. So suppose this is my metal, this is my insulator, this is my metal, this is my metal, 1, 2, and I am applying the voltage here. So if I raise the Fermi energy, then the electron can tunnel from one to another. So that is where they are used. Even this is the electron tunneling can also be used to develop field effect transistors, right? FETs made from quantum dots. So these can be used in also for the dielectric behavior. A large number of grain boundaries in nanocrystalline materials is expected to increase the dielectric constant. Right? For example, nanocrystalline Ti2 has a higher dielectric constant, so compared with coarse grain samples. This is due